All right, so I thought I'd do a little video review for you guys of units 4 and 5. I'll post this um, on the classroom. So anyway, back in units 4 and 5. So this is the reviews for unit 2 exam. The first thing we need to remember is what kind of variables were we comparing? So back in Unit 4 and Unit 5, I'm not really going to talk about Unit 6 because we just finished that. But Unit 4 and 5, we were looking at two quantitative variables. So height and weight, or shoe size and arm length, or hours studying and grade on test, right? So we were looking at two quantitative variables. We took out gender or whatever the categorical variables were, right? So when we're trying to determine which is the independent, which is dependent variable, we're wondering which one is changing with respect to the other one. Or in other words, which one are we trying to predict for? So if I want to find out hours studying versus grade on the test. Well, usually I'm trying to predict the grade on the test, so that would be my dependent variable. And it depends on hours studying, right? So that is my independent variable. And then when we were looking at the three different kinds of functions, we had linear, exponential, and logistic functions. And with linear functions, we had a constant rate of change. We called that the slope back in Algebra 1, but it's the increase or decrease in that function. Now, in statistics, we write this a little bit differently, but still, B here is my slope, and A is my y-intercept. So when I look at the formulas on the formula sheet, there's two of them. Number one is to find the slope, I take the correlation R, multiply by the standard deviation of y over standard deviation of x. Back in chapter 1, we learned how to find the mean, standard deviation, but that's the same standard deviation, but we have two of them. And again, if we need to remember which one is on top, actually it's on the formula sheet, never mind. And then B to find, or secondly, to find the y-intercept, we're going to plug in the mean of the y minus the slope, which we just calculated, times the mean of the x. And when we look at slope, what we're looking at is change in y over change in x. So how much did we rise over how much did we run, right? Rise over run, same thing. The y-intercept was the value of y when x equaled 0. What we remember from our studio was sometimes it didn't make any sense, like the world record in year 0 didn't make any sense because it was so far off the graph. And then third thing from linear functions was the residual, the actual y minus the predicted y. The actual y we got from a point like 310, and this is my actual y, 10, right? To get the predicted y, we would take that 3, plug it in, substitute it into the equation, and solve for y. When we got those two values, let's say we got the actual value of 10, the predicted value is 10.2, so the residual would have been negative 0.2. That's off the sheet. And that was predicting the y value based off of an x. All right, No, this is in the wrong spot, I see now. So second was an exponential function, right? And what we notice about an exponential function is the growth is constant. It's constantly growing. I should have sketched that, right? Linear up here, exponential. The slope is constantly changing. It's a constant change in the rate. So the rate is never the same, as opposed to this linear equation where the slope is always the same. It's a constant rate of change, and this is a constant change in the rate. All right, and when we look at the exponential function, we have four, I guess. We have A, which is the initial value, B, which is the growth factor, and you got to remember also that the growth factor is 1 plus the growth rate. And then the other variables are time, and then the variable we're trying to predict for, which is the dependent variable right here. And this is T is the independent variable. And generally time is always the independent variable. So look at a problem or a little example here. So if we have a 23% growth rate and start with $200, the equation is 200 times 1.23. Where did we get the 1.23? We add the rate plus 1. So 1 plus 0.23 is 1.23 time to the time. So if I want to predict how much money you would have in 10 years, we're just going to plug in or substitute into that equation 200 times 1.23 to the 10th power. Now, the other kind of equation we went backwards, right? So if we need to find out how long it would take to earn $500, that's when we had to use log. So we started out with 500 as our y, and we're trying to predict for t. Well, first thing we needed to do was divide here. We get 2.5 is equal to 1.23 to the t power. Then I'm going to need my calculator or some sort. I'm going to take log base 1.23 of 2.5, and that's going to be t. Now it turns out, go check that, it was 4.43, I think. 4.43. It's a terrible 4. 4.43. And then if I want to check it, I can just take that 4.43, plug it back in for t, and see that that equals 500. And then the last function was the logistic model. And the logistic model had a rapid growth, followed by a slowdown and a gradual leveling off. And you can see that down here in the graph at the bottom. I hope you can't see that. And in the equation, y hat is equal to c over 1 plus a to the negative t. Okay, so c is the carrying capacity. And a is, it shifted our graph left and right. And b was the rate at which the function increases, and reaches that value, or reaches that carrying capacity. So if b increased, then it just got to the carrying capacity quicker than it did in this one, right? And the point of inflection is always c divided by 2, the carrying capacity divided by 2. So if we look down at this little example here, looks like my carrying capacity is about 15,000. So divide by 2, I get 7,500. which would be somewhere in this neighborhood right here. And then I look down here at the x-axis and I can kind of find out when that was. There's also a function, I think it was natural log of A divided by the natural log of B that calculated that time, but I need to know what A and B were in order to figure out what that time was. So that was a brief review on Units 4, Unit 5. Unit 6 was all of the sampling distributions and basically the central limit theorem. And I guess while I'm at it, I'll just throw that on here. But the central limit theorem says that if we take many samples from a population and calculate their means and make a graph of those means, the graph of those means should be normally distributed as long as my sample size is large enough. The mean should be whatever the mean of the population is. So the shape should be normal. The center should be whatever the mean of the population is. And the spread, which is called the standard error, should be whatever the population standard deviation is over the square root of n. Now, with that being said, I need to go back and review z-scores, because in order to calculate any of these answers, I'm going to need to use z-scores, look up those probabilities in the standard normal probability table. And I guess while I'm at it, when you look up a value in that table, it's going to tell you less than. So, if you look up that answer and it doesn't look right, that's because it's a less than, and you're going to have to subtract from 100, or 1, in order to get the greater than if they're asking you to calculate the probability that somebody would be, or that 10 people would average more than, 6'2", or whatever it is. So then I'm going to have to figure up the probability, look up that z-score, subtract from 1, and I would find this probability over here. Now that's a super brief Unit 6 review that I didn't even plan to do, but that's all the content that's on the exam 2. And now, how to stop this.